So when light shines on this, it will generate a current through here. Oops, that's bad. So first we're going to have an inductor. And we're going to have a capacitor. So what happens is this will generate a signal like this. And then when this goes up, the current will flow this way. And inductors oppose changes in current, so it will flow this way, and capacitors do the opposite, so that
So
will do
far,
that.
okay. So far, I'm good.
And then when it's on the downstroke, the opposite will happen. This will do this, capacitor will do that. So at a certain frequency, these two will resonate, and after lots of complicated calculus, you get the frequency at which they will resonate is equal to that. So the frequency over here, what we're looking to filter out, is 12,000 cycles a second, but sometimes we'll need to do 600 cycles a second. That's later. So to get this, we need 12,000 equals 1 over 2 pi root LC, and then you just solve for root LC and then put in convenient values to get the 12,000, 1,200.
What do you need to get to 12,000?
1,200, because this is the frequency at which the signals are coming in. You might have other signals that are at different frequencies that you need to get rid of. So these will resonate and go up and down at the same rate to give a signal output when you measure it here at 1200 hertz if you set these to the correct values. And the ones I've been using are and 110 microfarads equals C1. So now sometimes we want to do 600 hertz, and we know that capacitors in parallel add their capacitance. So the capacitance of this entire circuit is equal to C1 plus C2. So we could replace this with a capacitor of C1 plus C2. So now, when we want 600 equals 1 over 2 pi root LC, 600 is 1200 divided by 2. So to divide things by 2, we want to multiply the bottom by 2, and because this is in the square root, we want to multiply C by 4. Now L stays the same because we have one here. We're just going to add another capacitor here. Call this C2. Now we want this C2 to be such that when we close a switch and add this into our circuit, it will change C of this equation to be 4 times what it originally was. So C2 equals 3C1, then C net equals C1 plus 3C1 equals 4C1 is what we wanted. So this is a value of 329.8 microfarads is C2. So, and then you just put a signal in here, and you can do stuff over here like amplify it and do other stuff. So what you do is, for example, I don't know if this will work. Okay, I'm doing a transient analysis, so, but yeah, this signal right now is 1200 hertz, and it's letting through the signal because it's at the right frequency. But theoretically, if we change this to be something else, let's change it to, I don't know, 400, it should be much less. And this is whatever. That's what they call it.
Oh, it's calculating now?
Yeah. Basically, I just entered this circuit into this equation here, and it does an analysis over time of what's going on. So, yeah, that's a big one. You can pause the recording.